All right, let's go and start. Just announcements where we're at. Sorry I did have a little bit, for a bit of time, I had the wrong thing, announcements up there. So we are doing ensemble learning. So these kind of go hand in hand with the decision trees that we talked about last time, because the most common kind of ensemble is an ensemble of a decision tree. So if you did the readings, we're looking at chapter 7 this week. But most of the stuff is about random forests, which is really methods of combining a bunch of decision trees. But they're not all, the same decision tree. It is important that they're kind of that they differ from each other. So anyway. We'll talk about that. I'm still working on getting the previous assignment returned back to people, so sorry about that. I have gotten behind on stuff. I'll try and get that back. I wanted to talk about that before the end of this week because you should be working on the assignment on ensembles, the assignment 5. That is due at the end of this week. I'll do the usual today and Thursday and pull that up. I'll probably pull that up for the last 5 or 10 minutes and discuss some more about the ensemble learning. We went over quite a bit of it previously, but as usual, make certain you're working on that. If you have questions, let me know. So I know I've had a few questions. A couple people are working on the assignment 5. We've got we are kind of getting to the last couple of weeks here, so there is one more assignment 6, which will be over the unsupervised learning stuff. So starting next week, we're going to get into talk about 2 or 3 weeks where we'll look at kind of a bit of a different topic than what we've looked at so far. So different ways of what's known as unsupervised learning. Also, just continue to try to remind people about the class project. Make certain you're making progress on that. I still haven't. I'm going to try and go back. I'm going to try and give a little bit of feedback to see where people are on that at some point. I still haven't got to that yet, but yeah, you should be trying to be doing a little bit of that regularly. So let me know while you're working on those if you have questions or want to discuss anything about stuff you're trying to accomplish on that. So we're going to be doing unsupervised learning. We are going to have a test 2. I'm going to have the test 2 during the actual last week of classes. So it'll be the same format. It'll be online. I'll have it open for probably like Thursday and Friday. I think that's what I did last time. So yeah, just plan ahead on that. And then the class project will be due actually during finals week, although it's the due date was like Wednesday or Thursday of finals week. But whatever due date I have in there should be the right thing. So I didn't give all the way till Friday of the finals week to finish up your class project, but you'll have a little bit of time after the exam 2 is due to finish up working on the class project stuff. So, all right. I should have. Let me go ahead and I should have had this started up here. I'm going to jump in and talk about our notebook on ensemble learning for most of the rest of the time here. Then we'll spend a little bit of time on the current assignment 5. See if there's any other stuff we should clarify. So some of the stuff on assignment 5 you had to read about bagging and boosting and some of the stuff in this chapter. So okay, give me a moment. Let me go and open this up here. Let's see, where is my... Oops. There we go. All right. Okay, yeah. So anyway, just as a reminder, so last week we had covered quite a bit. Well, I don't know how well we did it, but we did go through the decision tree, including talking about most all these things, the computational complexity of decision trees and how the cart works, and touched a little bit on like regression and things like that. So yeah, this week we're moving on to what we've labeled as the Unit 12 here, the ensembles and random forest. So this mostly comes from Chapter 7 of our textbook. Okay, so ensembles are kind of surprisingly can do quite well as classifiers in some contexts. So, especially the random forest kinds of things, because of the way they are created, you don't have to specify a lot of metaparameters, and they can be a good go-to to see if they'll do well on your problem or not. So, but yeah, before we get to random forest, the basic idea of an ensemble, I don't think it's most people will have no problem kind of understanding what we're doing here. Maybe the why of why we would do it or how it would work is a little bit subtle maybe. So if you read the textbook, it talks a little bit about why an ensemble can work. So it brings up some concepts like wisdom of the crowd. You might have heard about that sort of talked about it sometimes. So it is the idea that if we have multiple trained classifiers, so we'll talk about classifiers. You can do the same thing for regression as well. You can make ensembles for regression, but again, it's more of kind of a natural fit when you're talking about classification tasks. So if you have multiple classifiers, the easiest technique, if you want to try to combine them, is to do something like a hard voting classifier. So basically, I probably mentioned this previously, that the easiest idea is if we're just doing a binary classification, so the answer has to be yes or no. So if you have like an odd number of classifiers, one of them has to get, and you ask all of, like if you have 3 classifiers and you ask all of them to make a prediction for an input, you have to get one of the classes yes or no to have more votes than the other. So the simplest idea is just to train multiple classifiers and take a vote, right? And I want to talk about, so of course you have to, you can, so what you have to do for the assignment right now that you're working on is there is a scikit-learn method that you can use to build a kind of an ensemble by hand by training separate classifiers, actually by giving separate classifiers to an ensemble, and it will train it for you and do all the work of then combining the things, right? So, and if you haven't done the read, we'll talk a little bit about some of the things you can do that's a little bit more sophisticated than just sort of a straight up vote of your different classifiers to determine what your prediction will be. So, before I move on that, I mean, I'll talk a little bit about the why of why these can work. Okay, so if you did the textbook reading, this is, I don't know if this is a good argument. I don't know if it really convinces me or not, but this is again some more idea of how or why an ensemble might work. This example is taken directly from the textbook, just to explain it a little bit. So if we're flipping an unfair coin that has like a 51% chance of being heads, if we do individual coin flips, do some number of them, so like each one of these represents doing one sequence of 4,000, 5,000, 10,000 coin flips of this individual coin, and keeping track of the number of heads and the number of tails. So the ratio of heads to tails, or the ratio of heads to the total of flips is really what the ratio is here. Right? So you see that even after 10,000 flips, you can get some. It's really essentially a random walk. So if you know what a random walk is, that's all that's happening here. So some of them can be significantly, just by chance, can be quite a bit above 51%. Right? Some of them can be quite a bit below, right? Even after 10,000 flips, right? But the more you do for a random walk like this, the more likely it is that you're going to converge, that you're going to eventually get closer to the, your walk will end up somewhere hovering around the true ratio, the 51% here, right? So it shouldn't be any surprise that what we're ensembling here, I don't personally think this is a great example, but what we're showing on the dark blue here is we're ensembling all 10 of them, right? So this is effectively, as if we'd done 10 times as many, right? So, or another way of thinking about this is that once we're at 10,000, this is really more what you would expect to see after 100,000 flips, even if your random sequence for the first 10,000 was kind of the walk ended up above, quite a bit above, or quite a bit below, right? But I think that it does illustrate a little bit about what an ensemble of classifiers might be able to do, right? So more quickly it gets close, and you can rerun this, this bit of code, this example for you if you want to multiple times. You should pretty much always get the same result. The individual ones that are only doing 10,000, there'll be some variation, but the one that's really just the average of the 10 at each one of those points will much quicker get close to the true ratio, the true answer that's driving the model here, and will tend to converge pretty close to faster to the that true ratio. So in terms of using ensembles of different types of classifiers, like combining like a logistic classifier, support vector machine, decision tree, K&N, which is basically what I asked you to do for the assignment you should be working on right now. I think we'll go back and take a look at it. So I think I asked you to create 5 separate classifiers. I think it was those, and also like a neural network, like we talked about last time. So there's one thing that is kind of important. So for ensembles of diverse classifiers, for ensembles of classifiers like this to work, they really should be diverse. So they really should be, like this, you get diversity by using different kinds of classifiers. So that's one way you can get diversity. But even that might not necessarily be enough, although that can certainly help. So another type of diversity is by training them on random subsets, or adding some other kind of randomness in there. That's mostly what I'll say on this. So, but the idea is that if you have lots of these that our textbook uses the term weak learners. So kind of back to this more of like an analogy here. So the individual ones you can kind of think of as weak learners, or they're it'll take them longer to converge there. So even if they're relatively weak, as long as they're doing something to get a bit of the signal from the noise, and especially if they're diverse. So if they're here, this probably doesn't illustrate what we mean by diversity very well, like is discussed in the textbook. But as long as all of your weak learners are getting different parts of the signal, they're better at certain things than other things on whatever classification task you're trying to do. That is especially useful and important on building good ensembles, where multiple weak learners will actually combine to get a better result than any of the individual would. Right? So, okay. So, also a bit of a warning. So the task that you're doing for the assignment right now, you might not get real great results. So it's hard to get a data set that definitively shows kind of this ensemble effect working well. So yeah, I think again, I'll try to go back and maybe talk about it a little bit at the end of the class here, but I think you should get maybe usually a little bit of an effect, but don't expect something real real impressive in terms of how well the ensemble does versus the best of the individual classifiers that you do on the assignment. So hopefully you'll see a little bit, but maybe not necessarily anything really really big, significant kind of improvement. So. Okay, so moving on, but yeah, so that's what that example was meant a bit about, to discuss and think about how these ensembles work and why they might end up giving you something that's a bit of an improvement over any individual classifier that you might have. So, but I mean, these do work. So I encourage people, if you're interested, get into, like, for example, the machine learning competitions, like on Keras and things like that. So you'll often see that at the end of competitions like that, so once you get so far, kind of often a last step is to take separately built models that you have and combine them using an ensemble method. So often you can get like another percentage or two improvement in performance by ensembling good but kind of separate, different kind of classifiers. So it's a common technique that you'll see people doing to squeeze out a few more percentages of performance for a task. So. Okay, so let's move on to the basic. So the first part of the assignment that you should be working on right now, you do have to kind of create an ensemble by hand. So use scikit-learn. Its ensemble method to train separate classifiers and combine them. So here, after these plotting functions, this is the basic. So what you're doing in your assignment tasks. The first one should be pretty similar to this. So scikit-learn has a voting classifier for kind of building ensembles, but you don't have to train them by hand. You just specify a list of, we're calling them estimators in this context. So estimators or classifiers are kind of the same thing here in this context. So one of the basic things of the voting classifiers, whether you want to do hard or soft voting here. So that's another thing you're supposed to do on the current assignment. Let me rerun everything above here. So in this case, so the default for the voting type is hard. So that will just do a straightforward vote. So I'm not certain what it does in order to break ties or things like that. And this will also work for multi-class. So there's other stuff that we won't get into a lot of details of. But if you think about how you would implement this kind of voting by hand, if you wanted to do it for a multi-class classification, you'd have to keep track of the votes for each one of the different classes, and again, always have to, if you're doing hard voting, worry about if you end up with exactly the same number of the predicted class for a particular class, how you break a tie, that kind of stuff. So, soft voting, if I haven't mentioned it before, soft voting works basically, it's like a weighted average. Soft voting, the estimators that you give to the voting classifier, they all have to be able to return their predicted confidence or probability of what their prediction is of the class, right? So that is the that is, hopefully we gave, so here when we're doing soft voting, close that off yet. So so here we just use straightforward hard voting first in the example. You'll have to do similar things in the assignment that you should be working on right now. So after you, so I shouldn't have skipped ahead on this. So after we set the voting classifier, you can actually you don't have to fit the individual classifiers by hand. You can fit all of them at once by calling the fit method. That will fit the individual classifiers with the training data that you give it and the labels that you give it for a classification task. And if you ask to make predictions for the voting classifier, it will do the hard or the soft voting, right? So it'll combine the predictions that you asked for, right? But you can access the individuals inside of Ensemble. So there's lots of ways to do it. So here we're just taking advantage of the fact that when we actually passed it in as a list, so those classifiers that we passed in a list should be ones that get trained when we do the fit here. So we still have handles them, but hopefully we show that. There's other ways. You can actually also go through iterators. So your voting classifier. There's an attribute called estimators, so you don't really have to keep handles if you don't want to. You can use this also to get the list of the classifiers and iterate through them directly from your scikit-learn voting classifier class here. So for soft voting, the thing I wanted to say before I kind of sidetrack off talk about some other things is that all the classifiers have to support being able to specify the probability of their confidence for each of the predictions. So not every classifier does that natively. So for example, support vector machines don't do that for reasons that hopefully we touched on a little bit when we talked about support classifiers. I probably didn't talk a whole lot about it, but yeah, the basic support classifier, it can't easily give you its estimate of how confident it is when you ask it to make a prediction. So if you actually, you have to specify that you want it to be able to do that when you create a support vector classifier. And what that does, though, is it actually keeps track of extra information in order to come up with those predictions, right? So it's not really a native part of what a support vector classifier can do. It's extra things that it keeps track of it in order to. And the method in general is that one there. So I spotted it here from the reading, right? So this one, the basic predict method gives you the actual class that is the winner, that your trained classifier is going to make a prediction of if it's asked to predict which class. But this one will give you the its confidence, how probable it thinks for all of your different classes that you have. So, for example, we used predict in order to figure out the accuracy score here, but we could have done something like, so for example, for the support vector machine classifier, we could have asked for the probabilities for, again, say for our test data. So here, since we're doing a binary classification task, we actually get an array of predictions. So this is going to be the prediction that is the 0 class, the prediction that is the 1 class, right? So the predict is predicting 1 here and 0 here, because that had the highest probability for this binary classification task. But the probabilities is giving you an estimate of how confident it is, or how likely the model believes it is for each of the classes that you have and the things. So anyway, I'm spending a little bit of time mentioning that because also you need to use that. So that'll be one of the things you'll be using even in the last task for the current assignment. So when we build by hand an ensemble, we do ask you to do that using the probability outputs of the individual classifiers. All right, let me see here. So before I move on, let me look at the voting classifier one more time. So if there's any other parameters, it would be good to mention here for using this. So you've got your hard or soft voting. Soft voting will only work if all of the individual estimators support returning back the probabilities or the confidence of each of the estimates. So yeah, and you want to use the estimators. You'll probably need to use that at various points to get access to all the individual classifiers in an ensemble. So. All right, yeah. So I think that's the main things there. Okay, so after the first part of the assignment, so really up to this part is similar. You have to do similar stuff on the current assignment where you use the voting classifier from scikit-learn to train individual kind of diverse classifiers and do some stuff with it. So this is really the beginning then of talking about ensembles of trees, so random forests and other things like that. Okay, so another approach, instead of using classifiers that are diverse, that are all of different types. So yeah, in the previous example, we used 3 different kinds of classifiers. So a more common approach for ensembles is to use the same type of classifier, but just train them on a different diverse set of data, or adding some randomness into that. Okay, so so yeah, is to use the same the same estimator, so a bunch of estimators, but then you train them in different ways. So the easiest thing to think about that is to train that on just a random subset of the training data. So here, the second approach is you're trying to get diversity by the training process. So you can either break up the training set, or you can also do things by the metaparameters. So you can change the metaparameters in different ways as well. Just bagging and pasting, you might run across these terms in other contexts as well. So another place where you might see this is if you need to, if you have like a skewed data set and you need to artificially create some examples of one of the classes that's underrepresented, you can also do a similar thing where you do some sampling with some randomization. Okay? So yeah, sampling with replacement. So what we mean by that is when you sample a set of data in order to create a subset to train with, I could take the items out and then when I sample my second item, I wouldn't consider any items that I've already selected in my sample, right? So that's sampling without replacement. Or another approach is just to always have all the items that I want to sample from, and when I select an item, I don't remove it, right? So that's what sampling with replacement is. Or in that idea is if you take an item, so if sampling is just, I've got a set of items, I want to pick one at random, right? So that's all that sampling is. Without replacement, if I pick an item, I would remove it. So the next time I pick another item at random, it wouldn't be in the items under consideration. But if you think of it as with replacement, if I pick an item out, I put it back in the next time. So every time when I'm sampling from the whole subset. So the idea, what that kind of means in practice is that if you're sampling with replacement, I can actually, at random, choose the same item more than once. Whereas if you sample without replacement, I'll only ever get each item once. And if you sample with replacement, I can create a sample that's actually bigger than the set that I'm sampling from, but I'll have some copies, some multiple samples of the same item. Whereas if I'm doing it without replacement, of course, I can only at most get the same number of items before I run out. Right? So my sample subset that I create has to be smaller than the whole set of items that I'm sampling from. Anyway, so technically you'll run across this sampling with replacement is called bagging in some contexts. So I guess that's short for bootstrap aggregating. So I wanted to mention the bootstrap here because, again, some people, if you do have a skewed data set, you might, if you do, we don't really touch directly on it in this class, but this bootstrap aggregating, this kind of sampling, can be used in order to generate samples in order to even back up, so to remove some of the skew that you have. So it's often a good approach when you have a highly skewed data set that you're doing classification on to do some sort of bootstrap aggregating method. And anyway, so our textbook then, or in some people in some contexts, if you do sampling without replacement, they call it pasting. So. So let's just move on. You can actually build a bagging classifier by hand, and you don't have to use a decision tree. So you could do the same thing that we're talking about here to create an ensemble of support vector classifiers or an ensemble of neural networks, things like that, right? So here, I'm skipping ahead a little bit, but we show creating a ensemble using a bagging classifier of decision trees. This is really all a random forest is, right? So it's very common to do this with decision trees, and that's just called a random forest. And different versions, like the extra trees, are all the same ideas. It's an ensemble of decision trees. So here, for the bagging classifier, like we just talked about, what it's doing is we're going to create an ensemble of 500 decision trees. So we're actually creating 500 individual decision trees here. That's what the number of estimators parameter controls when we're doing this stuff here. Oops. And we're going to be using bagging here, so that's basically sampling with replacement. So in this case, sure, I kind of forgot. So we're going to be training this with our made-up data set that we're using here from this Moons data set, and I can't remember exactly how many. Let me just go back real quickly here. We had we had 2,500 samples, right? So this data set had 2,500 items in it. All of them I can't remember how many number of features there were, but and basically we're doing a binary classification task for this, so labeled 0 or 1 in this case here. So back to the bagging classifier. So for all of our 500 estimators, we're sampling, since we're doing basic bagging here, we're going to do the sampling with replacement, but each one of the 500 classifiers is only going to get a sample of 100 of the 2,500. Right? So it's going to get a relatively small sample of the data set that we train it with. Right? So the hope is that that will end up allowing us to have a diverse set of decision trees, so a diverse set of classifiers. So even though we're using all of the same type of classifier, they're all going to see a different portion of the data set when we train them. Yeah, so actually you always just use the bagging classifier whether you're going to do with or without replacement. So that's what the bootstrap parameter does. So by default it's true, so you're going to be doing what the textbook called bagging, so doing sampling with replacement. But you can also change that to false to do it without replacement. Yeah, we'll come back to those things, the out-of-bag evaluation stuff. So this can do surprisingly well as an ensemble, and in fact, it's common enough. That's again jumping ahead here a little bit, but that's really all a decision tree is having this kind of a voting ensemble of a bunch of decision trees where we're doing some sort of sampling for replacement to train all the individual estimators, right? And then you can do other stuff here where we randomize some of the meta parameters as well. So here we're also limiting. Remember the decision trees that we talked about last week, they will on the data set that you give them, if you don't do any regularization, they will create a decision tree that will perform perfectly on the set of samples that you give it. All right, so without this, each of these estimators would be able to give perfect performance on the 100 samples that we train it with, but still that necessarily isn't necessarily a problem, because even though they do perfect on the 100 samples they see, their results are going to be combined. If we want to make predictions on unseen data, right? So even though the individual estimators, if we hadn't specified something like this, would be overfit on that 100 samples, the ensemble might still do well overall, right? But you can also constrain the individual classifiers in this kind of an ensemble to also, limit the max leaf nodes or the max depth or some of those other stuff that we talked about last week. So yeah, this does pretty well if you compare this to previously. It's a reasonable decision boundary that you get for this ensemble here. So here we were comparing the results of having an ensemble of the 500 decision trees, right? So in fact, you probably get. It's more than reasonable. This is a pretty good looking decision boundary. This moons data here, we only had 2 features, I believe, now that we're looking at it, but it was pretty noisy. There was quite a lot of overlap, so there's no real good decision boundary on using these 2 features that will do real well, right? But this is relatively smooth. It's probably about as good as you can do. But you can compare that to the result of on a single tree, single decision tree. So this, we didn't do any regularization on the second example. So this is overfit on the data here. So you get a real kind of choppy thing, right? So while some of these things will, allow it to pull out and make correct predictions on this data it was trained with, those don't necessarily help the performance, for future data, for unseen data, right? So yeah, the point of that was the previous one will likely generalize much better with our ensemble of the 500 trees than the single decision tree that we did there. So. All right, let's finish up on the bagging classifier here. So one nice thing that you get with this kind of sampling is you can use that basic idea in order to get an estimate of how well the ensemble will do on test data, on unseen data. Okay, so the basic idea. So this out-of-bag evaluation is whenever we're doing sampling, just to be concrete, in our previous example, we had 500 trees, but each one was only trained on a sample size of 100, right? So they only had 100 items. So all the items that each one of the individuals were not trained with are called out-of-bag instances. So each one of those 500 trees has a large number of out-of-bag instances, so instances that they never saw before, that they weren't trained with. Okay. So really, if you've understood what we talked about previously in this class of splitting data into training and test data, That's all that's kind of going on here. So since we sampled, and since each of the individuals was only trained on a subset of all the samples, you can think of all the ones that it wasn't trained with as unseen data. So we can use those in the same way when we did a train test split in order to estimate the performance that the trained ensemble will have on unseen data. So you can get that directly from the OOB score, the out of bag score here. So so that doesn't give as good of a description as I was thinking it would. So what this gives you, though, is an estimation of how well it will generalize. Okay? So the way it's doing, the textbook hopefully describes this a bit more than this does here. So to come up with a score, it would figure out the performance, the accuracy, in this case, by using the data it was trained with, but calculating the accuracy for each of the 500 estimators that we had on their out-of-bag items. So if you set that to true, it will keep track of that, and it will calculate that. So this should give a similar result. It's a different way then of estimating the accuracy, your generalization, the accuracy on unseen samples, as we would get if we did a train test split, right? But just without having to split the data. Right? So we're just directly making that kind of an estimate on these unseen samples that we have, these out-of-bag items, as they're called here. So, okay, so yeah, let's move on. I just mentioned these. We'll probably I'll come back to this then on Thursday. So most of the stuff here in 7.5 is what you need for the very last part of the assignment here, where we talk about the boosting and the stacking, especially the stacking. Maybe the last thing I'll mention here is we didn't mention before, but the sampling that we were talking about was sampling all of the features, right? So, even if we have 2,500 samples, if we pick 100 of the samples at random, we're using all of the we only had 2 features for this moon's data set that we used here. But you can imagine, so another way you could do sampling is to sample by the features instead of by the by the rows, sampled by the column. So if you have a problem with, say, 100 features, 100 columns, you might try and build a classifier where you build trees that only use a random 10 of the 100 features or something like that, right? So that's really what the random patches is. And yeah, you can use the same bagging classifier to do that. So one of the hyperparameters allows you to sample by features by specifying the max features. That this bootstrap features allows you to do sampling with or without replacement, same way that the bootstrap does with or without replacement on the sample. This would allow you to do with or without replacement on the feature there. So. And you can actually do them both at the same time, so that's really what the random subspaces is. If you're sampling both some random features, I might have that backwards. So yeah, the way the textbook uses that is random subspaces is you're keeping all the instances but just sampling some features, and a random patch is where you're sampling both. So just some number of samples picked at random, and only a subset of the features of those samples are used. So again, sometimes it can be useful to sample on the features or to even do both at the same time. So you might sometimes get good results doing what the textbook called the random patches. So. All right, so yeah, we'll leave the forest, and I'll go into the details on, especially on the stacking then. I didn't have a whole lot in this notebook on the stacking here. But we'll go into the details on that on Tuesday. Let me just for 5 minutes bring up the assignment real quickly here. Again. So yeah, we did look at this a little bit last week. So up through the first 3 tasks are using a basic voting ensemble, and you're asked to try it out with both hard and soft voting, see the results that you get. So task 4, so I didn't talk about random trees specifically or random forest specifically, but all that's being asked in task 4 is to use actually either the random forest or the extra trees, your choice, and try that out, right? So all the stuff that we're talking about for the bagging and the pasting is really what's happening. That's really all that a random forest is. So it just does that for you instead of by hand specifying that I want a bagging ensemble where I use a decision tree as the estimator. Right? So if I do a random forest, it's just using the same thing, but the estimator is going to be a decision tree. And extra trees just does some things where it adds a little bit of extra randomness to some of the meta parameters for the decision trees they're creating. So yeah, the idea on this one was it's interesting to compare this to the performance that you get for the hard or the soft voting ensemble where you do it by hand for the previous task 1, 2, and 3 here. So, And then finally, so I will talk more about this on Thursday. The basic idea for stacking this data is, I think I did mention this before. So obvious idea is we might be able to get a little bit better performance if instead of just doing a simple method to combine all of the individual classifiers into a single result. So the voting ensemble is just combining them by taking the majority vote, or the soft voting ensemble, if I failed to mention that, is using like a weighted average, using the predicted probability times the number of votes for each one. So sometimes you can get some improvement, or even in some instances you get a real dramatic improvement by doing something a little bit more sophisticated. So an obvious idea is to take all of the individual classifiers in an ensemble, but instead of just doing a simple vote of some kind, to build a new classifier that takes the outputs of the individuals as inputs and gives the final prediction. Okay? So that's really what task 5 and 6 are. So task 5 is to create a function to help you easily stack a set of individual estimators' outputs into a new set of data that's suitable for training for a classifier that will basically combine individuals to give a final result. Right? So that's really what the create stack data, and that's really what stacking is instead of doing a simple vote, creating a new estimator that takes individuals as input, and you train it on their output to come up with the final prediction, basically. And that's what you're supposed to do on task 6. So the function on task 6 should be reusing the task 5 function. And again, you may not see much, if any, improvement on this, but it should do at least as well, if not maybe a little bit better than like the bagging classifier or the best, the soft voting ensemble that you do by hand in the previous one. So certainly shouldn't do any worse. You are supposed to reuse your functions. I'll talk about some more details of this on Thursday here, but you are supposed to be reusing your functions from like the task 3 that actually created the individual kind of ensembles and returned that as a inside of a single voting ensemble, and also reuse the create stack data in the task 6 stuff here. All right, so yeah, let's go ahead. That's it for today. I'll end it there. We've got a little bit more to talk about. We'll do it on Thursday. We'll get some more details on the stacking in these last 2 tasks here. If anybody has any questions on it, so yeah, I should be in office hours today. Let me know if you have questions. Do keep working on the assignment 5 that is due on Friday then. So. All right, that's it.